Mixed analog digital simulation using Pspice. Let me give a brief introduction on the importance of simulation. Simulating a circuit's behavior before actually building it can greatly improve design efficiency and provide us insight into the behavior of electronic circuit design. We can also evaluate the timing behavior of our design as a function of component propagation delay tolerances. These component propagation delays are generally obtained from manufacturer specification sheet for the components we have used in our design. However, in cases where some of the parameters are unspecified, Pspice can establish the missing values by extrapolation, that is calculating values outside the range of known values. To illustrate this, I have built a mixed analog digital circuit using a sinusoidal 1 kHz voltage waveform at the input, which goes into an op-amp, a non-inverting op-amp which has a gain of 11. Hence the output obtained at V01 would be plus minus 11 volt at 1 kHz frequency. This output is then given to a Zener diode which does function of clipping. Hence the output at V clamp which we obtained will be plus 5.6 volt to minus 0.7 volt. This is given to a Schmidt trigger whose output will be a square wave from 0 to 5 volt at 1 kHz. This is then given as an input to a clock signal of the 74393, which is a ripple counter. Counters is a device which stores the number of times a particular event or process has occurred in relationship to clock signal. What I have used today is to create a decade counter using this simple ripple counter module. A decade counter is one that counts in decimal digits rather than binary. Counts from 0 to 9 and resets to 0. Counter increments on each clock pulse until it reaches 1001. When it increments to 1010, the input goes high, which will clear the counter to 0. Because this is a ripple counter, some glitches may occur in logic systems connected to their outputs due to slight delay. This ripple counter usually advances on the falling edge. In order to simulate the counter, we go to analysis, do setup, and in the transit analysis we do the print setup to 1 millisecond and the final time is 19 milliseconds to run 19 cycles. Then we go to digital setup. This dialog box will allow us to specify timing and initial conditions for digital circuits. The default initial stage is generally X, which we set to all zeros, because if we keep it to all X and run simulation, which we will see, the output appears as double lines. This can be seen when we run the simulation circuit. As you see, the output appears as double lines. This is because of if Pspice does not know the initial state, it cannot determine any of the following states. Hence, we need to define the initial state to all zeros. The different timing modes are available over here. Minimum and maximum can be used as it relies on observing circuit behavior only at the extreme of specified tolerances. However, worst case is considered to be superior than minimum and maximum, as it will help you identify situations where the timing of the signal is critical to the proper operation of design. Also, using minimum, maximum or typical allows signal propagation through digital devices to be represented as instantaneous transitions, while in case of worst case, the effect of individual component delay ranges are propagated throughout the circuit. The default A to D interface is level 1, which will strictly map logic levels onto changing input voltage. Level 2 is generally for A to D interface transitions directly from 0 to 1 and 1 to 0 without passing through any of the intermediate stages of rise time, fall times or unknown state. So when we do our setup with timing mode as typical and initialization all 0, and we simulate our circuit. This will ideally give a voltage. This will ideally give a counter working from 0 to 9 and resetting after 9. As you can see from the graph, this is the clock signal that we received from the Smith trigger. The output from A would trigger with will invert at every clock signal. The output at B will go high when A goes from high to low, that is from 1 to 0, and so does C. It goes high when B goes from 1 to 0. Now when we put the trace of all the sinusoidal voltages that we have attached to prove our point, we got to V01, which is the voltage after the operational amplifier. Vin was the supply, and V clamp was the output from the Zener diode. As seen, the supply voltage is plus minus 1 volt sinusoidal voltage. The output of the operational amplifier after multiplying gain by 11 volts will give us output of 11 volts, while the output from the Zener diode will be plus 5.6 to minus 0.7 volts. Now if we run our circuit in the worst case situation, we will see how our circuit reacts. To do this, we again go to digital setup and make our timing mode as worst case. To simulate this, we just calculate and do our simulation. As can be seen, there are two error messages that occur. This means the circuit has calculated some propagation delays, and it will show accordingly whatever the worst case situations was. Worst case can thus be considered as perhaps best, or else can best be thought of as a tool that can tell you whether or not your digital design will operate as expected under the worst possible combination of component delay tolerances. To conclude, I will say simulation generally allows us to replicate the actual behaviors of our electronic circuits before we can implement it. Electronic simulation software can thus engage a user by integrating them into a learning experience. Thank you for watching this video.